Now, how much fluid flows across a boundary? If we have two solid walls, top and bottom, and some boundary surface here in between, and the flow is moving mostly from this direction to this direction, from A to B, then everywhere along the surface there's going to be some flow crossing the boundary. It might be crossing in this direction, or some of it might be crossing in that direction, and it really depends on the distribution of velocity. So we'll need to integrate over the entire surface, and we can start that out by looking at one small chunk of surface. To take this little piece of surface here, if this is the overall velocity vector, so it's not perpendicular to the surface, then we can take the component perpendicular to the surface. That's this V perpendicular, and it's at a right angle to the surface. It's just a component of the overall vector. Now, the best way to get the component of a vector if you're doing vector algebra is to take a dot product with a normal vector. So if this is a normal vector, it's 1 unit in magnitude, it's perpendicular to the surface, and in this instance it's pointing this way. The convention is to always have a unit normal vector pointing out of the surface. So we're looking at the flow going into region B, so the unit normal vector is pointing out of the surface away from region B. So the volume flux coming into region B at this location is negative because it's the opposite direction of the normal vector. The dot product of the velocity vector and the unit normal, or just the V perpendicular, this component here. That's the volume flux. That's the amount of volume that goes through this surface per unit area of surface. And it's just a velocity component. Now, volume passing through a small area dA, so a little chunk of surface here has a small amount of area dA, it'll be negative V dot n times the area. So we'll go from a flow, volume flow per unit area, to just a volume flow by multiplying by that incremental area, or just the perpendicular velocity times that incremental area. So if we want to get the volume flow through the whole surface S, this whole surface, then that volume flow has to be equal to negative, that's this negative right here, or that one right there, integral over the whole surface, from this surface up to that surface, of V dot n dA. Now, the details of what the surface is shaped like will tell you how to formulate this part of the integral. If we're looking at the volume flow through a flat surface, it's going to be a lot easier because we're looking at just the component, and if the flat surface is parallel to the flow direction, and we just have flow in one direction, and we have an average velocity V, then the total flow, volume flow, is just velocity times area. If we don't have an average velocity known to us, or if we have a velocity distribution, then we'll have to actually do this integral.